Hello everyone, this is Ujjwal Agrahari from Team Code, and the topic for our presentation is word lookup using Trie and hash table. So which basically demonstrate how we can search and retrieve words or string from a collection of words using two distinct data structure, that is tree and hash table. So talking about the word lookup algorithms, they are indeed crucial in modern computer science as they play a significant role in improving software performance, especially in tasks like text search, spell checking, autocomplete, and data retrieval. So basically in these demonstrations, we are going to make use of the two data structure, that is the hash tables and the trie, and we are going to make use of the comparisons of these two data structures, and we are going to demonstrate how we can use this for efficient word storage and retrievals. So talking about the trie data structures, a trie data structure is a tree-like data structure that is particularly efficient for storing and retrieving word or string with a complexity of the O of L, so where L is the length of the word. So it is especially useful to tasks like autocomplete and searching for words with a common prefix. So talking about the how data is represented in the trie. Trie is composed of nodes where each nodes represent a character in word. The root node is typically empty and each character in the word is represented by the child node. So each node may have multiple children, one for each possible character in the alphabet. The end of the word is marked by a special flag indicating that the word is present in the tree. Proceeding with how an insertion takes place in an trie. To store a word in a trie, we can start from the root word and traverse the tree and creating new nodes for the character that are already not present. So let us say that we need to store a word and. So what basically we will be doing, we will be starting with the root node and then we search for the word A. If the A is not present, then we will make a node and store the A in it. And after that we can search for the word N, and if the word N is not present over there, then we can make a node and insert the word N. And similarly we will do the same functionality for all the words present in the node. And for the other word, let us take consideration of the word and. So here what we will do, we will search for the word A, and since A is already present, so we will go to the node A. After that we will be searching for the word N, and since N is already also present, then we will move up to the word N, and after that we will search for the word T, and since it is not present, then we will create a node and insert the value T in that. So this is how insertion in a tree take place. And talking about how we can retrieve word in the tree. So to retrieve a word from a tree, we start from the root, traverse the tree following the characters of the word of the targets. So if we reach the end of the word and find the end of the word flag, this means that the word is present in the tree. This is how a trie works, and which we will be using to implement our problem statements. And talking about the another data structure that we will be implementing, it is a hash table. So hash tables or hash maps are another data structure that can be used for the word storage and retrievals. So they are generally useful for fast key value lookups. And talking about it, it is an array like a structure that stores the key value pairs. The key are hashed using a hash function and to determine their index in the array, and in the each index in the array can hold the multiple keys value pair, often called as a bracket. So talking about how the data is stored in a hash table. At first, to store a data word in the hash table, we hash the word to determine its index and insert into the corresponding bucket. So let us take our consideration of the following examples where the key value pairs in the key there is a string of the numbers. So what we will be doing is we will be subjecting the key to a certain hash code, will result in a certain type of the values for taken consideration of the word SpongeBob, and we will make use of the hash code hash function, which will then convert the SpongeBob into a specific number. Let us say that is the 48625. Then we will be operating it with the modulo operator with the parameter as the size of the hash table. Then we will get the value as the 5 and add the value of the 5 in the array. We will be storing this value. So this is how insertion in a hash table will take place. And talking about the retrievals of the data in the hash tables, we will be basically following the same scenarios which we were performing in the insertions. So at we will be making using the keys, and we will be converting it to the hash code. We will get the index, and once we get the index, from there we will be retrieving the values. So that's all about the theoretical knowledge about the data structures we will be implementing to obtain the solution of our real life problems, that is the word lookup algorithms. That's all.
Okay, hello everyone. I am Utsav Jaiswal from the team Code, and now I'm going to be explaining the code files that we have used in this project. So this is the code file named as trie.cpp, as you can see in the file name. Now this code defines a C++ program that implements a simple dictionary using a TRIE, simply known as trie data structure. A trie is a tree-like data structure as discussed by Ujjwal before, which is used for storing and searching for words efficiently in our program. Now we first start by including the necessary header files for this program. IOStream is of course used for input and output in C++. String is used for string operations. Unordered map is actually a library in C++ that is used to create a data structure to represent a trie using a map and character node mapping. So we are going to use a map that maps a character with a trie node, which is defined as a structure in our program later. And include fstring is done to import the txt file which stores all the words that we are going to include in our C++ program. So now we move on to the structure trie node. So we define a trie node structure. This structure represents a node in the trie structure. It contains an unordered map, as you can see here, which is defined in this header file highlighted red. It contains that unordered map which will map each character of a certain word and keep it as a trie node, as we saw in the implementation of a trie structure, and that unordered map is known as children here. Then we have a boolean variable named as isEnd of the word, and as it is self-explanatory, it marks if that letter or if that trie node is actually the end of the word. Now we move on to a constructor of this trie node class, which will simply set the isEnd of the word to false by default, and we can set it to true as per our requirements, as we will see in the further processes. So now we have a class named as trie. As the name explains, it will be representing a dictionary that contains a pointer to the root of the tree, and that root of the tree is present as a private data structure, a private data member throughout this class. So that is how we also maintain abstraction in this program. Now the public members are the constructors. So there's only one constructor yet in this trie data structure. It is named as trie. So this constructor will simply set the root to a new trie node. So a new trie node will be created, and using this trie node constructor, it will simply set the isEnd of the word to false. So that's how it is done. Now we have two member functions. The first member function is void insert. So insert is a function that returns a type void and takes the input of a string named word. So what does this insert function do, right? Insert simply inserts the word into the trie data structure by iterating through the characters of this word and creating nodes as needed. So we'll get the current node as the root, and for each character in the word, if this is not the end of the word, which is what this if statement is doing, if the find will simply return and the ending of the children data structure if it does not find the C anymore. So this means if it is the end of the word, then we will simply create a new node. Otherwise we will set the current pointer to the next letter in this word, and after all of this process is done, the current will be reaching at the point of the word in which it points to the last letter, and we know that last letter of the word is the end of the word, right? So the current pointer will have its data member is end of the word to true. So as we saw, is end of the word is used here. Is end of the word will simply mark the end of the word. So when this current runs through this whole loop, so it has run through all the characters, we will finally set current which is the last letter at this point, to the end of the word. Okay, now we move on to another another function in this class trie. That function is named as search. As the function's name signifies, this function will be performing a search about this string named as word throughout this children, which is a data structure contained within this trinode structure. So this will return true or false, which is known as a Boolean variable. If it returns true, then it will make sure that this word is found in this current dictionary. Then if it returns false, then it says that it is not found in this dictionary. Now, how this function basically works is that the search method is used to check the entered word exists in the dictionary, right? So depending on the result, whether the program prints a message indicating whether the word is found in this dictionary. As we can see in the main functioning, we use this search function, and this will determine whether it is in the dictionary or it is not in the dictionary. Okay, so let's see how the search function works. So first of all, we'll just initialize a trie node to the root. So this root will be the first node in this entire trie data structure. Then we will select this word, and for each character in this word, we will see that if it is the end of the word, so if character that we have seen in this word, if it turns out to be the end of the children, then we will return false, because in this case the children has ended before we have found the end of the word. So if our word was something like BATMAN, Batman, but if the dictionary only found the word BAT without including MAN, this means that the word is not present. In that case, we will return false, and this is what this if statement signifies. If this is not the end, then we will simply go and check the further letters. So let's say that BAT and our dictionary also had MAN, so our dictionary had Batman, right? So if we have reached the point T and we find that T is not the end of the word, it has some more letters, let's say it has M, then in that case the current will simply move to the next letter. That's what it is doing. And after it has searched through all the characters, this means that the word has successfully been gone through every letters. So every letter of the word has been iterated through this children data structure, which is a trie. So if that is the case, then we can simply return current is end of the word. Why we are not returning true is that maybe the word is Batman hero. This is not a real word, but maybe this is the word. But our query for the word was Batman. This means that the word is not found in this dictionary, right? So if the current position of this current trie node is the end of the word, that means our word is found. So that's how the searching works. Now we move on to the int main, which is the simple part of this program. So we simply define an instance of this class dictionary, and it is of the class trie. So we'll also initialize a file name dictwords.txt. The significance of this file name is that we have a file named dictwords.txt, and this dictwords contains about 3000 words, sample English words, that are most frequently used, and we will initialize a file stream input file with this file name, which is present in the same directory as these code files. So if we somehow don't manage to open it, then we will display an error message and we will end the program. This is just for the concept of error handling. Now next we have our word. Then we also have while standard get line input file word. So this means that while we still have words in this input file, which is this dictwords.txt file, we will insert each word to our dictionary, which is the trie data structure. So we have inserted all the nodes in this entire txt file containing different words into this dictionary, and that is the whole role of this input file. At that point we close our input file as it is no longer needed. Then we have a string variable named as search word. This will be storing the user query. So the user gets a prompt saying enter the word matches and to search in the dictionary, and that will be stored in search word. If dictionary dot search, and it will perform this search on this search word, so we know that search is actually a boolean returning function, right? So if it returns true, that means the search word is in this dictionary, else it is not in this dictionary. That's simply how the query method works using a trie data structure. So that's how the trie data structure works. Now we move on to the next file, which is hashmap.cpp, which is the alternative way to store words and perform queries using a hash map instead of a trie data structure. So this code defines a C++ program that creates a custom hash table, and it is used to build a dictionary. This program will allow the user to search for words in this dictionary, and here is a breakdown of the code. So we include the header files iostream for input output. Vector is used in this program in the following series. Then we have a string header file which is used for string operations. Actually, this header file is duplicated, so we can simply remove it. There we go. And we have also included fstream for the similar purposes as we have seen in this previous code. So now we first define a class named as custom hash table. So this class will represent a custom hash table having a fixed table size. So this table size is currently defined as 100. We can choose appropriate size as per our requirements, and it uses a vector of strings. So this vector of strings is known as table. It is a nested vector, as we have studied in our previous classes. Now it is used to store the data of our program that can hold multiple strings. That's why if we only needed one vector for storing millions of strings, then we could have simply used one vector of type string, but we need a vector of multiple strings of multiple categories as well. So that's why we have used vector nested inside a vector, and that vector will contain the strings. Then we have the public part of this program, which has a custom hash table constructor, which will simply perform the resize function, and this table it will be resized to our table size. So now we move on to the member functions of this class. So we have the hash member function, which is returning int type. So this is a custom hash function that is used to index for the key. What is the key? The key will be the strings that we need to put inside our functions. So this is a custom hash function that calculates an index for a given string by summing up, this is the main part, by summing up the ASCII values of its characters, and finally it will take the modulo of that summation value with the table size. So we had the table size of 100. Now this will simply add up all the ASCII values, and that will be modulo 100. That is how this one works. So this hash value will be returned by this hash function. Now we move on to the insert function, which is quite a simple function. So void insert, as it returns void because we are only performing insertion and not returning any kind of values. So void insert taking a constant string key. We have marked constant because we don't aim to change the state of this key at any cost in this program, and that is simply a good coding practice. So we have this int index. The index will be storing the hash value of this key. That hash value will be given by this program. That's how they work in a union. So now then we get the table which is the nested vector structure in our class, and it will get this index, and at that index it will push back the key, which is the string. Now the next function is a boolean function named search. It also takes the same key as previously mentioned, and it will again get this hash value of this key. Then this will search for a key in this hash table by calculating its hash value, right? And then it will check if that key exists in the corresponding vector at that hash value. So this for constant string item in this table index. So we got the index here, and in this table vector and this index, if we have this string, then we will return true. But if we have somehow already searched through every entry, but we still haven't found the string, unfortunately, then we will be returning false. This is how this entire class and its data member functions work. Now we have the main function, which is quite the simple part of this program. Let's remove this comment before we operate. Okay, so we have defined a dictionary of this custom hash table. So this is the instance of this class, and we have a string file name the same as before, the txt. We open the file, and if it can't open, we return an error message for error handling. Then we also have a word, and for each word in this input file, we will insert this word, and then we close the input file. Actually, let's see how the dict_word.txt file looks in real time. This is the dict_words.txt. It has different entries of the English words arranged in alphabetical order. So there are millions, thousands of words, hundreds of words. They will all be added to our dictionary. So after they are added to our dictionary, we can simply close the input file, and the fstream is closed. Now we again prompt the user to enter a word to search in the dictionary, and it gets the search word in this variable. And if it can find this search word, which will be returning a boolean value of true if it is able to do so. If it is able to find, then we can simply say that the word this is in the dictionary, else it is not in the dictionary. So that's how this code file works as well. So these two code files, they are the main cores of our project, and this is how they have been operating throughout this project. Thank you.
Now let's quickly see the output of our program. I'll first search the word in hash table. Okay, I search for a word table. See, when I search for a word table in the dictionary, what we can see is the word is found in 1.321 seconds, which the execution time. The word is found in 1.321 seconds. Okay, now let's search for the same word using try. Okay, see, I entered the same word and it took only 0.689 seconds. So we can see significant change in time, significant difference in time when we implemented try and when we implemented hash table. So why is why is this happening? So the basic and the most significant reason is this one, search function. In case of try, what it does is it searches for some common prefixes. If the common prefix is found, then it will quickly eliminate one path and we can entirely search in the path where the common prefix is found. But in case of hash table, what it happens is we are implementing the hash table in such a way that the word is searched for the entire hash table, and when it is found, then it is returned true. That means if there are multiple collisions, what it will happen is it will take significantly very longer time, and we need to implement some other mechanisms like chaining mechanism to solve that issue again. So we'll not go deeper into that, but basically what we'll understand is in case of searching in hash table, it will search in the whole entire hash table, and if there are collisions, then it will significantly increase the time complexity and it will become like worst in most of the scenarios if there are collisions. But if there are no any collision, then the hash table will map single word to unique location, and in that case, the time complexity can be constant in some case as well. But in case of try, as it searches for the common prefixes, so we can entirely eliminate a one path and we can simply search in the path where we find the prefixes, and it will significantly reduce the time to search the word. So now let's see the observation. Moving on towards the observation of try approach at first. In base case, the space complexity of try approach is big O of n, where n is the total number of characters in words. In base case, we assume that there are no common prefixes and each word has unique path in the try. So we will need n nodes to store n characters in the word, leading to a time space complexity of big O of n. In worst case, the words will have same common prefix, but we will need to store the words in n number of nodes only. due to which it will lead to a deeper trie, and we have the space complexity of big of n. Talking about the time complexity of trie approach, in best case, we will need to traverse the characters till m times, so that we will, if the character is not found, then we can immediately terminate the execution and return that the word is not found in the dictionary or word is not found in the trie. Then, talking about the worst case time complexity, in worst case, we will need to traverse entire path in the trie till m nodes. We will need to traverse. If m is the number of nodes, then till last node we have to traverse, and we will require to traverse m times in order to search for the word. So that was about the time complexity and space complexity of trie approach. Now moving on towards hash table, moving towards the observations of hash table. In case of best scenario, we'll have big of n space complexity. Even if there are no collisions in hash table, the words in hash table will map to unique location in the table, and we will have linear space complexity. Also, in worst case, we will have big O of n, because in worst case, all words will hash to the same index, which will lead to a single bucket with all the words. So we'll have to store n words. So big O of n is the worst case space complexity of hash table. Talking about the time complexity, here is the noticeable change in the time complexity of hash table, which is constant time complexity if there are no collisions. If there are no collisions, then word will directly hash to the correct location, and we will get the word in one go. So best case time complexity in case of hash table is big O of one, which is constant. It is really very faster than any other approaches. And talking about worst case time complexity of hash table, we will need to traverse till k times in order to find the words if there are multiple collisions. We will need to search through all the words in same bucket, and we'll need to find the target word in worst case. Now, moving on towards the differences between these two approaches, hash table has better time complexity in best case scenario where there are no multiple collisions. If there are no collisions, then as we saw earlier, that we can find the word in one go. In constant time complexity, we can find the given word by mapping directly to the unique location. In case of tries are more space efficient in best case, since the paths will do not have common prefixes will already be eliminated, so it will avoid the redundant storage of common prefixes, and we will have comparatively less space requirements in case of try. Also, the next point is about the hash table can have unpredictable worst case time complexity due to collisions. If there are multiple collisions, then the worst case time complexity of hash tables can be really time consuming to find the word. But in case of tries, it is predictable and it is mostly same in all the scenarios. So next point is about CP uses. This is a major point to look into while talking about try and hash table. In case of CP uses, the try data structure, what it does is it while searching for a word, it involves character by character traversal. That means we will have to do multiple comparisons and branching operations, which will add noticeable CP uses. Whereas in case of hash table, we can use hash function to directly compute the index where the key is stored, and it will not require any character comparisons during the search process. Also, the CP uses may depend on factors like depth of the tree. In case of try, the depth of the tree might be equal to n in case of worst scenario, which will result in more traversal steps and comparisons, and hence increasing the CP uses. Therefore, which data structure shall be used? See, the answer to this question is completely scenario dependent. If we have minimum space requirements, then we can go for tries. Tries will completely eliminate one set of path for searching and will only search in one path. So that can provide better efficiency for our program by decreasing the complexity to linear complexity in case of time and in case of space. While talking about hash tables, it can it can go up to constant time complexity in best case, and in worst case, the time complexity can be increased. If there are multiple collisions, then the time complexity will get worse in case of hash tables. But if there are no collisions and we are so sure about that, then we can go for hash table as it will perform really quick. Also, the choice depends on how much memory we can allocate and how can we handle the potential collisions in the hash table. That means we can use various techniques like chaining mechanisms in order to handle the collisions in hash table. By doing so, we can increase the efficiency of our program by decreasing the time complexity. That was all from our side. Be sure to like the video if you were able to gain something from our project. Do not hesitate to put your suggestions in the comment section and subscribe to the channel. Thank you. See you next time.